Assalamu alaikum, students. Are you able to hear me? Okay, good.
Yes, we can.
Okay, before starting the lecture, I need to once again just remind you or finalize that the two exams for the dynamics that we are going to take, both the sections will be together, your section and Dr. Salim's section. And the exam will be on Thursday. The first exam will be on Thursday, October 22nd. That is 8th week. Okay, from 2 to 3. And the second exam will be in the 13th week, November 26th. It will again be Thursday from 2 to 3. Is it okay? The class leader, yes. Good. Just wanted to confirm that because I was sending the timing to the Vice Dean of Academic Affairs. I just wanted to confirm that. Okay, so today we are going to start chapter number 14. We are already done with chapter number 12 and chapter number 13. So chapter number 14, what we are dealing with. So right now we are dealing with study of dynamics of particles. So chapter number 12 to 15 are study of dynamic of particles. Out of which chapter number 12 was the kinematics of particles, and chapter number 13, 14, and 15 are the kinetics of particles. Okay, for the kinetics of particle, 13 was using the force acceleration method. That's already done. We are already done with that. Now let's move towards the work and energy principle, chapter number 14. This is again kinetics of particles. Okay, so let's discuss about the work of a point force. Okay, so suppose there is a force which is applied at a certain point. So then we call it as point force. So let's say this is a point and force is applied at this point. So work of a point force. Let's say this point is P. Okay, so it is force into distance. But we also need to consider if the force and distance are at the same angle, in the same direction or not. Okay, so if they're making certain angle theta, then it will be the projection of force in direction and the displacement. So it will be Fp, which is the force multiplied by the displacement S multiplied by cos theta, which is the angle made between them. Okay. This theta, when theta is 0, then UP is the work of a point force. This work is positive. So when theta is 0, this work is positive. When theta is 90 degree, this work is 0 because cos 90 is 0. Okay. Example of theta 90 degree, work of a normal force. Okay. So normal force, suppose if I have a surface and I have a body, okay, which is resting on the surface, or let's say the body is moving on the surface, because of the weight of the body, there will be the normal force of the surface on the body. But since the body is not moving in the direction of the normal force, or so the direction between the normal force and the motion of the body is actually 90 degree. Since this is 90 degree, that means the work done by the normal force is 0. Okay. Then if when theta is 180 degree, then up, or the work done by the point force, will be negative. So when does it happen? The example is the work of the friction force. Friction force always acts opposite to the motion. So if the body is moving in this direction, then the first friction will be acting in the opposite direction. So the force is in this direction, but the motion is in the opposite direction. So that means theta is 180 degree between force and displacement. So that means up is negative. Okay. So before moving forward, work of a point force. Does everybody understand that? Is there anything within this that anybody do not understand? Is everything clear or not? It's clear. Okay, so that was the first type of work of a point force. Now let's discuss the second type of a work of a weight. Weight is a force, you know. Weight is a force. It has unit Newton. Okay, so whenever the weight is there, so let's say if I have a body, and the body, there is certain weight of the body, so there is a direction. Okay, and the direction is downward because the weight acts towards the ground. Now suppose if the body is also moving down, then the work done by the weight, or you can say uw will be positive, because the motion and the force are both in the same direction. But suppose if the body is moving up, weight is still acting down, but the body is moving up, so the work of the weight will be negative. So when moving up, uw is negative. When moving down, uw is positive. And what is the work? Work is the force, which is the weight itself, multiplied by the vertical distance. Here delta y is the vertical distance. Okay, it has to be vertical. That's the vertical distance. Okay, so that's the second kind of work. So first kind of the work was work of the point force. Second kind of the work is work of weight. Before moving forward, is there anything within the work of the weight that you do not understand? Is everything clear? Good. So here, this is important. You see, I put here in the bracket positive and negative. Why? Because we need to make the decision ourselves, is this work positive or negative? When the object is moving down, then the work is positive. We make the decision. When the object is moving up, then the work is negative. We make the decision. Okay. Anybody want to ask anything? Everything's just clear. Your hands should be on the computer or on your mobile or wherever you're listening, because I need responses from you all the time. That okay, is it clear or not? Okay, good. Okay, so two types of work we discussed. One is the work of a point force. Second is the work of a weight. Let's discuss a third type. Third type is work of a spring. I call it US, capital US. Okay, so for the case of the work of the spring, the formula is half K S2 square minus S1 square. Okay. But you see here, this is a big problem here in this book. I told this thing before you as well, but now you're going to see this. Uh, they use S for stretch as well as S for displacement. This gets sometimes real confusing, but you need to just look into the problem to check that what S are we talking about. Look here. When we say S here, S2 square minus S1 square. So we're talking about a spring. Okay. So let's say this is the spring. Okay. Say this is a spring. Okay. So spring, this is, let's say this is the original length of the spring, L naught. Okay. Then what we do is that we stretch the spring, and now the new length of the spring is this, capital L. Okay. So S is the stretch, which is L L minus L naught. H is a stretch, which is L minus L naught. Okay, so here this S is this and this stretch, final stretch, initial stretch. Okay, however, when we were talking here up FP into S, this S was not the stretch, this S was the displacement. So same symbol for different things, and this gets a bit confusing many times. Okay, so but just keep that in mind, that wherever we are dealing with the problem, just you have to look into the problem, that what variable are we looking at? Is it a distance, is it a displacement, or is it the stretch? Okay, remember here this S2 and S1 are the stretches. They are not L naught, they are not L. They are not L naught, they are not L. They are stretch. Initial stretch, final stretch. Okay. So, so we have the formula here, US is equals to plus minus half K S2 square minus S1 square, where plus minus is something that we need to decide. Is the work positive or negative? Okay, so let's have a look at it. Suppose I have a spring initially L naught, okay, and what I'm doing is that I'm stretching the spring. When I'm stretching the spring, the motion of the spring is in this direction, but the spring itself is applying a force to resist the motion. Spring is applying a force. We're talking about the force of the spring. The spring is applying a force to resist the motion. So the motion and the force are in the opposite directions. So when you are stretching, US is negative. Before moving forward, is this point clear or not? I had a spring, now I tried to stretch the spring. When I'm stretching the spring, so I'm moving the spring in this direction, but the spring itself is applying a force in the opposite direction. Because this is the nature of the spring, it tries to return back to the original position. So the force of the spring will be opposite. So the force and the motion are in the opposite directions. So the work done is negative. Okay. The next thing, now let's say that the spring is already stretched. Now let's say the spring is already stretched. Now I release it. I release it. When I release it, what happened? Now the spring is moving back, but at the same time, the force of the spring is also in the same direction as the motion of the spring, because it is moving back to its original position. So when it is de-stretching, so when I release it, so the motion of the spring and the force of the spring are both in the same direction. So work done is positive. Do you understand this point? Is it clear? If it's not clear, don't be shy. You can ask. It's better you just open the mic and ask me if you have a problem. Okay. Okay, so let's discuss about the other way. Let's say that I have the spring and I compress it. Okay, so this was original and now I compress it. Okay, so I compress it. So when I'm compressing it, the motion of the spring is in this direction, but because of the compression, the spring will apply the force. The force of the spring will be opposite to the motion. We will try to return back. So the motion of the spring and the force applied by the spring will be opposite to each other. So when compressing the spring, US is negative. You understand that or not? Is it clear? Good. If anybody feels that it's not clear, you can ask. Okay. Okay, now let's discuss it. Now the spring is compressed. It's already compressed. Now what I do is that I release it. So now it start decompressing. It's returning back to its original position. So the motion of the spring is in this direction, and the force of the spring is still in the same direction. So the force and the motion are both in the same direction. So the work done during decompressing is positive. Got it? So when I'm stretching, work done negative. When I'm de-stretching, the spring is returning back to its original position. Work done is positive. When I'm compressing, work done is negative. When I'm decompressing, the work done is positive. Is there anything within this that anybody do not understand? You can ask. Is the concept clear here? What is this all about? To make a decision whether it is positive or negative.
So, doctor, if we can't say is positive or negative. Depends on else.
We can say it as well, but this confuses the students a lot many times. Okay,
But
so what I do is that what I do is that I say that for S2 and S1, don't put it as initial stretch or final stretch. Put it as higher value minus lower value. So this should always be positive. And then
okay.
make a decision about positive or negative yourself by looking at the problem. Is it stretching? Is it de-stretching? Is it compressing? Is it decompressing? Okay,
Okay, it's clear.
it's clear.
Yes.
Anybody else has any question you want to ask? Okay. So this was very good question by you, because this was the next thing I was about to tell. Because since we are making the decision ourselves that whether the work done will be positive or negative, so the value here after calculation should always be positive, because here this decision of the sign we are making it ourselves. Okay, so for the stretches that we have S2 and S1, always make higher value minus lower value, so that this value is always positive, and then make a decision whether the work done will be positive or negative yourself by looking at the problem, whether it is stretching, de-stretching, compressing, decompressing. Okay, if this is clear to everybody, then let me clear the drawings. So we studied three types of work done already. Work done by a point force, work done by the weight. Work done by a point force, it's cos theta, that's going to decide whether it's going to be positive, negative, or whatever it is. Work done by weight, when you need to make a decision yourself, is it a positive or negative, based upon if the object is moving up or down. Work done of the spring force, work done of the spring, you need to make a decision yourself whether it's positive or negative based upon if the spring is being stretched, de-stretched, compressed, or decompressed. Okay. Then we have a fourth type of work, which is the work of friction. Work of friction, it's always negative. This is what we say, that in case of the point force, when theta is 180, that the example is a work of friction force. So work of friction is always negative. So always negative, multiply by the force, but the force for the friction is what? It is mu k into n. Okay, that's the force of friction, mu into n. N is the normal force. Multiply by s. S here is again the displacement. Okay, don't get confused with this s with the s for the spring. Okay. So four types of work I have discussed with you. Work of a point force, work of a weight, work of a spring force, work of friction force. We discussed all the formulas. Is there anything within this discussion that you do not understand? Please ask. Is everything clear so far or not? Okay, everything clear. Good. Good. Okay, so this is chapter number 4 we are discussing right now. I have actually discussed all the important points here with you. So the dot product, when we talk about the work, so dot product is AB cos theta. It's a scalar quantity, not a vector. Okay. Work of a force, we just discussed that. Okay. When theta is 0, when theta is 90, when theta is 180. Okay. The unit of work is joule. Okay. So it's Newton meter. It's force multiplied by the distance. The unit of work is joule. English unit is pound foot. Okay. Suppose if the force is varying with the displacement, it's not constant, then you have to put into the integral sign f cos theta ds, s1 to s2. Okay. Work of a weight, we just discussed that. When positive, negative, we discussed it. Work of a spring force, we discussed it. Okay. When positive, negative, we discussed it. Okay, khalas. Let's see the problem. There's a lot of theory written before, but I have discussed all the important points which are important for the numericals. You can go through the theory yourself if you want. Okay, so okay, khalas. Let's see like this. A 10 kg block shown in the figure rests on a smooth incline. Okay. You do understand every word matters here. Okay. So we're gonna see everything in detail. 10 kg block. So it's a block 10 kg shown in the figure. So that's a block. Okay. Rest on a smooth incline. So you see there's a word smooth here, and smooth has a meaning. Okay. If the spring is originally stretched 0.5 meter, Just focus over the words. If the spring is originally stretched 0.5 meters, so originally the spring was already under stretch. How much it was stretched? 0.5 meter. Determine the total work done by all the forces acting on the block when horizontal force P 400 Newton pushes the block up the plane 2 meter. So you see here, this was the original position. Let me just expand it. Okay. So this was the original position of the block. Okay. And at this point, the spring was already stretched 0.5 meter. Then a force of 400 Newton applied over the block, make the block to move 2 meter on this inclined surface. Okay. So we need to find what is the total work done by all the forces in this problem. Okay. So first thing is that we need to draw the free body diagram, because we need to figure out that what are the forces acting. Okay, so if you just look at it, so we have the body, and a force, horizontal force of 400 Newton is acting on it. There will be the weight of the body which will be acting downward. Okay, the weight will be making angle of 30 degree from the normal to the surface, because this is making angle of 30 degree here. Okay, there will be normal force acting on the body. Okay, and there is a spring here. Okay, so there will be force of the spring. So these are the forces. Since this is a smooth plane, so there is no force of friction. Otherwise there might be force of friction as well, but since this is a smooth plane, so there is no force of friction. Okay, first of all, do you understand the problem statement here or not? Is it clear or not? Okay, so let's start solving. So what kind of works are possible here? We have point force. Yes, we have. This is a point force. So we have a work of a point force. Then we have the weight of the body. Yes, we have. And there is motion in the vertical direction. Yes, we have. So there will be the work of the weight. Then we have a spring. Yes, we have. So there will be work of the spring. Then we have friction. No, we don't have. So since we don't have friction, so there will not be work of friction. So three of the things will be there. Okay, one is the work of the point force, the other is the work of the weight, and the third is the work of the spring, but the work of the friction will not be there. So far so good, understandable? Okay, so now let's see each and every work step by step. So work of the force, we know the force FP. Yes, this is P, 400 Newton. We know this force, point force. We know this. Okay. Now, how long this point force? So you see here, the motion is in this direction, is on the incline, but the force is making certain angle with the motion, right? So force and motion are not in the same direction. Okay. So the distance that covered is 2 meter inclined. So we know that S is 2 meter, but this is not making, this is not at the same angle. So there is a specific angle between the two. And how much is that angle? That angle is this theta. So this is theta is 30 degree. So we know the theta. So we know theta, we know S, we know FP, we can find everything here. So point force, work done by the point force we can determine. Is it clear so far? Okay, good. Now let's see the other work. What do you think? The block's moving up or down? This is a big problem with the Zoom lectures. Cannot get the answers from the students directly. Anyways, no, the block is moving up. Look, the force is applied in this direction. Force is applied in this direction, it will cause the block to move up the incline. So the block is moving up, right? So when the block is moving up, what do you think? The work done by the weight, would it be positive, negative? Negative, true. Because the weight acts in the downward direction and the block is moving in the upward direction, so they are opposite to each other, so it will be negative. So first decision that you made is that it is negative. Okay, then the weight, it's known, right? 10 kg block, so 98.1 Newton, so weight is known. Can we determine that what is the vertical distance? Remember, delta y is not the total distance, it is the vertical distance only. Can we determine what is the vertical distance? We know the total distance is 2 meters. We know it is making at an angle of 30 degree. So 2 sine 30, sure. So this will be delta y. Okay, so work done by the weight. Is it clear or not? Good. Okay, let's move towards the next thing. Okay, work of the spring. What do you think? What's happening? Is the spring being stretched, or it is being de-stretched, or it is being compressed, or is it being decompressed? It is stretched. Yes. It is, no, not de-stretch. It is stretched. It was already stretched, but you are stretching it even more. It was already stretched originally, but you are stretching it even more. Okay. So it is being stretched. Since it is being stretched, so what do you think? Work done negative, positive? Negative. Perfect. So we make a decision that the work done here will be negative. Half K value is given. See here, K value is given. So we know the K value. Okay. Now let's talk about S2 and S1. Remember, S2, S1 are the stretches, not the total length. These are the stretches. Okay. So it was mentioned in the question that initially the spring was stretched 0.5 meter. So they mentioned it in the question that initially the spring was stretched 0.5 meter. So S1 is 0.5. Do you agree this or not? Okay. Now, once this once the block has traveled 2 meter on the incline, what do you think will be the stretch? S2 exactly. It will be 2.5 because originally the spring was stretched 0.5. Now you make the block to move 2 meter away again, more. So the total stretch now will be 2.5. Okay. So S2 will be 2.5. So it will be 2.5 square minus 0.5 square, and that's how you calculate it. Okay. So uh, is there anyone who has a problem in understanding that how did we calculate the work done by the spring force? You can ask. Good. So we know how was the work done by the point force. We know how we calculate the work done by the weight. We know how do we calculate the work done by the spring force. There is, because it is a smooth plane, so there was no work done by the friction force. So that's the only three forces we have. Just add them all together and you will get what is the total work done in this process. Okay, so let's see the solution here. Uh, okay, so you have P is 400, F, so 402 cos 30, so that will be the work done by the point force. Then for the case of a spring, okay, we make the decision ourselves that it has to be negative. Okay, and then it's half K S2 square minus S1 square. S2 will be 2.5, S1 is 0.5. Work of the weight, we make the decision ourselves, it has to be negative. So it is weight into 2 sine 30. So we have work of weight, where weight will be negative, spring force, work of the spring will be negative, work of the point force will be positive. Add the three together, so this will become this minus this minus this, so that will be the total work done. Problem solved. Is there anything in the solution of the problem that anybody do not understand? You can ask. Is everything clear so far? Okay. Can you repeat why the work of weight is negative? Look, okay, sure. See, the block is moving up. When the block is moving up, that means weight is acting down. Weight is acting down, but the motion of the block is up. So motion is against the direction of the weight. Okay, so when we talk about vertical distance delta y, so that delta y is in the opposite direction to that of the motion. So that's why the work is negative. Work of the weight is negative. Is it clear? Okay. Anybody else has any question? Good. So let's move ahead. Principle of work and energy. What is the principle of work and energy says? The principle of work and energy says that T1 plus summation of all the work done is equals to T2. But it says that T1 is basically what? They represent T as the kinetic energy. Kinetic energy is half mv square. Okay, so T1, whatever the initial kinetic energy, so what it means is that the velocity of an object will not change until some work is done on the object. So you have to do some work on the object, so the velocity of the object will change. So let's say the initial velocity of the object was v1, so initial kinetic energy will be half mv1 square. The final velocity of the object is v2, so the final kinetic energy will be half mv2 square. And the two things are going to be different if there is some work done, and the work done could be in four forms. It could be a point work done by a point force, it could be a work done by the weight, it could be the work done by the spring, it could be the work done by the friction. Okay, so what the principle of work and energy says is T1 plus summation of all the work done is equals to T2. Or if we write it, it's half mv1 square plus summation of all the work. Just a minute. Yes. So this is T1. Okay. Then summation of all the work is, these are the four works that we have. Work of point force, work of weight, work of spring, work of friction force. Summation of all the work force. So kinetic energy, initial kinetic energy plus summation of all the works is equals to final kinetic energy. Okay. Do you understand this equation or not? Is there anything within this equation that anybody do not understand? Is everything clear so far or not? I've not done anything. Whatever we discussed before, I've just written that. This was the work of the kinetic, this was the work of the friction, this was the work of the spring force, work of the weight, work of the point force. Summation of all these things, this is the total summation of work done. This plus initial kinetic energy is equals to final kinetic energy. Is everything clear so far or not? Anyone who has to ask anything? Okay, so let's go like this. Okay, so principle of work and energy, just discuss that. Blah blah, discussed it. Discussed. Okay. So let's directly move towards the numerical. Okay. Do you want a break right now or you want me to continue? If you want a break, we can have a break of 10 minutes, you can say, and then we can continue. I wish I can get an answer. Continue. Thank you. Okay. Um, Example 2. Okay. When s is equals to zero point 0.6 meter, you see here, I told you they're going to make things difficult. So here, s is what? Focus here in the problem. S is the displacement here. But when you are going to use for the spring, then you have to keep that in mind, that S is also the stretch. So just you need to keep that in mind, that where you are using the S. Okay. So because they have this book have this problem, they use sometimes same variables for different things. Okay. So when S is 0.6, so here S doesn't mean the stretch. Here S means this distance from this end to the center of the block. When S is 0.6, the spring is not stretched nor compressed. So you see here, when S is 0.6, S is 0, S1 is 0. Do you get my point here? Is it clear? Okay.
Yes.
Okay. So when S is 0.6, the spring is not stretched nor compressed. And the 10 kg block, the block is 10 kg, which is subjected to a force of 100 Newton. So there is a force of 100 Newton, okay, has a speed of 5 meter per second down the smooth plane. Find the distance S when the block stops. So the thing is that a force of 100 Newton is being applied over the block. So the block is going to move down, but the spring at the same time is being stretched and pulling the block back. A time will reach when the block will stop. A time will reach when the block will stop. Initial speed of the block is 5 meter per second. But when the block will stop, the velocity of the block will be 0 meter per second. Okay. So we need to find that when the block will stop, let's say the block is stop at this point. When the block is stop, what is this distance? S. This is what we need to find. So initial S is 0.6. Final S, we don't know. We need to find, for initial distance was 0.6. Final distance, we don't know. We need to find it out. Okay. And that would be when the block is going to stop. So initial velocity of the block, 5 meter per second. And final velocity of the block will be 0, obviously. So before moving forward, I need to know, do you understand the problem statement or not? Is it clear? Okay, good. So we can apply the principle of work and energy. Let's do it one by one, okay? So first of all, do we have a point force here? Yes, we have a point force here. So this thing will be there. Is the object moving up or down? So object has a specific weight, so work of weight will be there. Yes. Is there a spring? Yes, there is a spring here. So work of the spring will be there. Will there be friction force? No, it is moving down the smooth plane, so no friction force. Okay, so let's cut it. Okay. So this is the situation that we will have. Okay. So now let's do it one by one. First of all, mass is given 10 kg. So here mass is 10 kg. Here mass is 10 kg. Initial velocity given, has a speed of 5 meter per second. So V1 given. Final velocity, we need to find when the block stops. So final velocity is also given. I will say given because I know that it should be 0. Okay. So now let's have a look at each and every term. First term, what will be the force, what will be the work done by the point force? We know FP, okay? FP is F 100, okay? We don't know the distance S. This is what we need to find. If you know, this is what we need to find, okay? And cos theta will be, we know theta is 0 actually, because the force and displacement are both in the same direction, right? So cos theta is I mean theta is 0, so cos theta is 1. So we know this thing. Okay. Is this point clear so far or not?
Clear.
Okay. Now let's talk about the work of the weight. Do you think the block is moving up or down? Down, exactly. The block is moving down. So what do you think? Work of the weight positive or negative?
Positive.
Positive. Perfect. So it's going to be positive. So weight is known, yes, because it is 10 kg. We know the weight. Okay. Can we know the vertical distance? We don't know the distance that is going to be covered. We don't know the distance that is going to be covered, but we know that it is on an inclined surface with an angle 30 degree. Okay. So it has to be whatever the distance, let's say the distance is S. So S sine 30 will be delta Y. Will be S sine 30. Before moving forward, do you understand this point or not? Is it clear? Good. Is there anyone who thinks you don't understand why I put S sine 30? Okay, good. So this thing is also clear. Now let's move towards the spring. What do you think? Spring is stretched, de-stretched, compressed, decompressed? Initially, it was not stretched. Initially, it was not stretched. So it is now stretched. So what do you think? Worked on positive, negative? Negative. Perfect. So now we know that it is negative. Half K value is given? Yes, it is given. K is given. Okay, S2 square minus S1 square. Now, who can tell me what is S1?
0.
Oh yeah, I wrote it there. Okay, good. S1 is 0. S2 will be the S. You get it? That is how much it is stretched. S2 will be the S. Okay. Yeah, you can say that because look here, we will call it S, considering that, let me just be consistent with it. Okay, we will just call it S because here we were calling everything as S. Okay, so the work of the block, we say it's weight into into distance sine 30. Okay, so we call it S. So here it will be S. In the end, whatever S we get, we have to add 0.6 into it to get what is the total distance. You remember, you have to just follow here what we are doing. For example, for the case of point force, just follow me here. When we say S, so S was the distance from the original point to the final point. Okay, S was the distance from the original point to the final point, right? So here, when we say del y, we say it moved to S distance sine 30. So it was from the original point to the final point, but in the vertical direction, so S. Okay, so here we say that S1 is 0. Okay, so we are not taking it from this reference. We are taking it from the initial point. And S2 will be just S square. Okay, in the end, now in this equation, S is unknown, so you're going to find S, and then this S is actually the stretch that went from original point to the final point, and it asked that what is the distance S when the block stops. So distance S is from this reference, So this reference is initially here, S is 0.6. So you're going to add 0.6 to your answer. So that will be your final answer. Okay, so you can do it like this, the way I have mentioned it to you, or you can do it the way it is done in the book. If you do the way it is done in the book, this is also correct. But in that case, you're taking always from the S from the reference. Okay, so here FP into S into cos theta, where S will be now this distance, which will be S plus points S minus 0.6, or you can say S2 minus 0.6. Okay, so work of the block will be S2 minus 0.6 into weight into sine 30. Work of the spring, then in that case you will say it is S2 minus 0.6 square, because S1 minus 0.6, because that is 0, S1 is 0. Okay, so in that case you will directly get S2. So both ways are correct, whether you do it like this or that. Okay, both is going to give you the same answer. Is the solution clear to you or not? Okay. Is there anything within the solution which is not clear to anybody? Just remember one thing. I wish the book has used a different variable for the distance than compared to the stretch. Okay, then it would become, things will become much easier. Okay, to understand. But sometimes students get confused in it, that where we are using S as a distance, where we are using S as a stretch. Okay, in the formulas here you always have to use S as a stretch. Okay, but here S is the distance. Okay, I'm using the same symbols because I'm just following the book so that you can actually follow up with the book. Is there anything which everything is clear so far or not? Okay, good. So let's move over to the next problem. The 3,500-pound automobile shown in the figure travels down the 10-degree inclined road at a speed of 20 feet per second. So we have the initial speed. So the initial speed is 20 feet per second. We have the mass or the weight of the object. Okay, and it traveled down a 10-degree inclined road. If the driver jams on the brakes, causing his wheels to lock, okay, how far as the tires skid, okay, on the road, the coefficient of friction between the wheels and the road is mu k equals to 0.5. So the thing is that this automobile was moving down the road, and then the driver suddenly put the brake. So now this automobile is going to slip, it's going to skid on the road. Okay, and eventually is going to stop. So we need to find how long does it move before it stops. So initially when the brake was placed, the driver was moving at a speed of 20 feet per second. So we know what is the initial velocity. And we need to find when the driver stops. So we know what is the final velocity. We know what is the weight of we know what is the mass of the automobile. So M is known. Okay. First of all, in this problem, do we have any point force? No, we don't have any point force. Okay. Yes, the automobile is moving down the inclined plane, so there will be the work of the weight. Is there any spring? No. Okay. And yes, there will be the force of friction. Okay, so it's like this. So for the initial kinetic energy, final kinetic energy, things are very clear. There's no problem in it. Okay. So now we're gonna deal with the other things. Okay, weight and the force of friction, work of weight, and the work by the friction force. Okay, work of weight. Do we know the weight? Yes, we know the weight. Do we know del y? Okay, first of all, is the automobile moving down or up? Down. So it should be positive or negative? Positive. Perfect. So positive. We know the weight and del y. We can find the del y, right? So whatever the distance it traveled while skidding, let's call this s. So s sine 10. S sine 10 will be del y. S sine 10, okay, will be del y. So let's discuss about mu k. Okay, so here we have the coefficient of kinetic friction. N is the normal force. Do we have that? We don't have that, but we can find it by using the uh, balance of forces. We'll do that. S is, again, we don't know how much is the distance moved by the automobile when it was skidding, so this is unknown. So here in this question, S is unknown and N is unknown. But for N, what do we do is that we can find N by making the uh, force balance in the normal direction. So since the automobile is moving like this, okay, so there is a weight of the automobile which is acting in the downward direction. There is a normal force which is acting perpendicular to the surface, perpendicular to the inclined surface, okay, and there is obviously the friction force which is acting opposite, okay. So we can actually find out what is the normal force. So if it will be NA minus 3500 cos 10, okay, equals to 0. So we can find what is the normal force. So if we have the normal force, we can just substitute the normal force here and then we can find what is S. So solution is done. Is there anything within the solution which you do not understand? Is everything clear? Looks, this solution is done by two ways. One way was by using the work and energy principle, and the solution is started and finished till here. Okay, so this is chapter number 14, methodology. The same question is then repeated by using chapter number 13, methodology, and is done here below by using chapter 12 and 13 methodology, and will end up in the same answer. So you can go through this part yourself, but it is just solving the problem again, but using chapter number 12 and 13 concepts. Okay, so if anybody solved like this or anybody solved like this, both are correct. Anybody has any questions so far? Okay, good. Let's move ahead. Okay, this is a problem. You can go through it yourself. Let's see this problem. The 40 kg boy, a boy is 40 kg in this figure, slides down the smooth water slide. So you have a water slide here. Okay, it's a water slide and it is smooth. So it's a smooth water slide and he slides down this water slide. If he starts from rest at A, initially at this point A, the boy was at rest. Determine his speed when he reaches B. So we need to find what is the speed of the boy when he reaches B, and the normal reaction the slide exerts on the boy at this position. So first of all, do we know the initial velocity? Yes, we know
0.
it, because he started from rest. Do we know the final velocity? No, actually this is what we need to find. This is what we need to find, P2. Okay. Do we know the mass of the boy? Yes, we know. Okay. Is there any point force here? No. There's no point force here. Will there be work of the weight? Yes. Is there any spring here? No. Is there any for work of the friction? Yeah, it should not be there. Otherwise the boy will be dead. So there is no work of the friction. There is no work of the spring. There is no work of the point force. Alhamdulillah. Question is easy. Okay, so boy is moving up or down? So work done positive, negative? Positive. Perfect. So weight of the boy is known. Okay. Can we know that what is del y? The vertical distance is actually given in the problem, right? 7.5 meter, it goes down. So we know what is del y. So just substitute it. So that's it. We just substitute it and we can find what is the final velocity. So the final velocity of the boy will be 12.1 meter per second. Okay. And the next thing we need to find is a normal reaction the slide exerts. Okay. For that, we can take summation of forces in the normal direction. We can do the summation of forces. Okay. Clear. Okay, so we can do the summation of the forces in the normal direction. So the free body diagram, when the boy is at point B, will be the weight of the boy will be acting down, and there will be the normal force acting up. Okay, so NB minus weight of the body, weight of the boy will be equals to MAN. So mass is known, and the normal acceleration is v square upon rho. So v square velocity is, we already determined the velocity. What is the velocity of the boy when he is at point B? This we can find out because the equation of the slide is given. This path where the boy was sliding, it has an equation y equals to 0.075 x square. So y as a function of x was given, so we can find out what is the radius of curvature. Okay, so we have to use this formula: 1 plus dy by dx square power 3 by 2 divided by d square y by dx square absolute. So we just substitute the values, solve it, and we get rho b, and then we just substitute this rho b here, and we get what is the normal reaction. That's how we solve the problem. Is there anything that you do not understand in the solution of the problem? Please ask. Is everything clear so far? Okay, good. Okay, this problem, go through it yourself. So I will go through with you guys with this problem only, and then chapter 14 part 1 is finished from my side. Okay, example 7. This is a marble having a mass of 5 grams fall from rest at A through the glass tube and accumulate in the can at C. So this is a glass tube and they fall. So marbles has the mass of 5 grams, fall from rest at A. So at A, the velocity of the marble is 0. And then there's a glass tube. They move through the glass tube and accumulate in the can, in this can at C. Determine the placement R of the can. Okay, so we need to find that what should be the position of the can uh, from the end of the tube and the speed at which the marbles fall into the can. So what would be the speed when the marble fall in the can? Neglect the size of the can. Okay, so again we can use, okay, now we have 3 points here, point 1, point A, point B, point C. Okay, so what we can do is that first of all we need to find what is the velocity. We can find the velocity of the ball at C by by applying the principle of work and energy between point A and C. Let's say if we apply between point A and C, so we know the velocity at A, right? Is 0. We want to find out the velocity at C. Okay, the mass of the can is known. Sorry, mass of the ball is known. Mass of the ball is known. There is no point force. There is no spring. There is no friction. It's just the weight. And since it is going down, so it will be positive. So we know the weight multiply by del y. It's given what is the total vertical distance. So we know what is del y. So just substitute everything and we'll find what is the velocity with which the balls fall in the can. Now, if you want to find that what is this distance r, so we need to solve the projectile motion. This is a projectile motion. We need to solve this projectile motion. For solving the projectile motion, it is better if we also know what is the initial velocity here in the projectile. So we can solve between point A and B using principle of work and energy. It's again the same way, only the distance, only del y will be different because del y between A and B is not 3 meters, it will be 1 meter because A is 3 meters from the ground, B is 2 meters from the ground. So difference between A and B will be 1 meter. Okay. And so we will find out what is the velocity at point B. Okay. And then after that, we can apply the laws for the projectile motion. We have the equations for the projectile motion. So we can use the equations for the projectile motion to find out what is the placement R. So that's it actually. Is there anything which is not clear? Everything is clear so far? Is everything clear? If anybody wants to ask any question, you can ask. So the rest of the slides, go through it yourself. So chapter number 14, part 1 is done. So if anybody want to ask anything, you can ask. Otherwise, okay, just a minute. Doctor, we can find recorded lectures. I'm not actually recording the lectures, but actually the lectures are not getting saved in my computer because I don't have space that much. Like 10 lectures, if we save, we need 1 gigabyte space. So, but anyways, it's if suppose if you want or if the students want any help session, so we can arrange another meeting on Zoom to provide you the help session if you want. Okay, so anybody wants to ask anything? Okay, that's it. Then today's lecture is finished and meet you next time. Thank you.